So hello AP Chemistry students. This next section of the equilibrium lecture outline is going to be short, not too long, about what we call heterogeneous equilibria. And what that basically means is that we have forms of matter that are different from each other. So the first thing that's really easy to understand is that when we write equilibrium expressions that include reactions that have solids and liquids in them, you kind of just get to ignore them in any equilibrium expression that you have to write, because both of them, solids and liquids, essentially have a constant amount. You don't have to worry about their concentration. And so what it does for us, and this is the part we like so much, is that if I see an expression like this that's got a solid in it, notice I've got solid right here. When I write the equilibrium expression, I have this lead ion. I've got some chloride ions squared because they have a 2 in the coefficient. But yay, I don't have to worry about the solid lead chloride. We'll see this in another chapter. These are sparingly soluble salts. If you like to think of it this way, you could have written the expression, but you could have just made the concentration of the lead chloride 1 in the expression, and then basically it just disappears. So the beauty of heterogeneous equilibria is that they will disappear in the expressions, making your life way easier. So here's a picture of a classic sort of equilibrium situation. We have some solid calcium carbonate, and that's pictured right here in the beaker on the right-hand side. We can see some solid calcium carbonate. We have some solid calcium oxide right here. And if you let these guys just sort of like open them up, have a sealed container, because that's the definition of equilibrium, the vessel has to be sealed, then you'll get the production of carbon dioxide gas. Notice that the amount is not really critical. And you can see in this one we have less calcium oxide and more calcium carbonate. So as long as some of each of those remain in the system, the amount of carbon dioxide that will remain above that solid stays the same. So one less thing to worry about. Let's do some practice writing equilibrium constant expressions. And as I look at the balanced equation I've got up here, I've got a liquid right here, which gets to be omitted from the expression. And in the second equation, I've got a solid and another solid. So when I write these, it's very easy. Here is carbon monoxide gas all alone on top of the equilibrium expression numerator. Here is carbon dioxide and hydrogen gas in brackets, representing the concentrations of those guys at equilibrium. Now, one thing I noticed though is that they are all gases, and technically we could have written a Kp, I guess, but for right now this will work. And if someone had given you the molar concentrations of those three substances, you could have calculated the equilibrium constant. Even simpler on part B, we have two CO2s in gaseous forms. That's why it's squared here. And, oh, sorry about that. We have tin solid, so I get to omit the tin in my expression. Don't have to worry about him. I've got tin oxide here, don't have to worry about that one. And so I have CO2 squared divided by carbon monoxide squared, because there's a 2 in that expression, and that's how we deal with heterogeneous equilibria. So it's really actually a pretty simple kind of way of thinking about it. Just think solids and liquids are essentially 1 in the expression and can be omitted. Now, I don't really want to do this problem. If you want to take time to look at it and read about it, go to sample exercise 15.7 in the textbook. I didn't see much value in the analysis of this particular problem. So where that takes me to is the end of this little mini session about equilibrium that are heterogeneous. And I'm going to stop there and call this a day on that mini part of the equilibrium lecture outline on heterogeneous equilibria. Okay, see you guys later. Bye.